Today I'm going to talk about semiconductor. In that one specific topic, which is PN junction, which tends to confuse me a lot every time I read it. If you ask me about it after a week, I'll have no idea what the fuck you might be talking about. So in that case, I'll watch this video and I will absolutely destroy you in that discussion. So first, we obviously need to talk about what a p-type conductor and what an n-type conductor is. They're both extrinsic semiconductors, meaning which you're using a dopant to decrease the energy gap between its conduction band and valence band. So basically, in p-type conductor, you're using a trivalent impurity. So you're having only 3 electrons of the dopant, and you have 4, like say we're using silicon, so you have 4 electrons, valence electrons, and they will bond with all of them. But the thing is, this electron will be free to move about. This is the intrinsically generated electron, meaning which this is generated only by the silicon itself. So it is not that good for our conduction, but what this is doing is that it is able to create holes. It's able to create more holes. Holes become the majority carrier in the p-type semiconductor. What's happening in the n-type semiconductor is you have a pentavalent impurity, and you still have only 4 over here. So these 4 will be able to bond, and the bond between this and its parent atom becomes very weak. So this is able to move around freely, and this is able to increase the number of electrons totally. So what you're doing is you're adding the extrinsically. Fuck it, I can't pronounce it. I'm just gonna say X and I'm gonna say in. So the X electrons plus the in electrons are the total number of electrons being generated, and some of the in electrons will actually go and bond back, like it'll collide with the hole that has been created by like the in hole that has been created, and the holes will get further reduced. Now, okay, so basically the thing you need to remember is in n-type, electron is the majority carrier, and in p-type, holes are the majority carrier. Now when you talk about p-n junction, the first thing you need to know is how it's made. So obviously you can't just take a p-type conductor and you can't take an n-type conductor and you just join it and you get a p-n conductor. No. p-n junction, no. It needs to be joined at the atomic level, like at 3 Amstrad, 5 Amstrad, which is not possible for us obviously. So what we do is that, say if we took a p-type conductor like this, we'll take some pentavalent impurity and put it on this side, just a little bit. So what will happen is on this side, on the right side, you get some n-type conductor properties, and on this side you get p-type. So you get a p-n junction basically. So what happens in this p-n junction? So there's 2 things we need to talk about: the diffusion and the drift. So what's happening is that we know that p-type has holes and n-type has majority electrons. So because there's holes here and there's electrons, from n to p electrons will move, and now because there's a negative charge that is going towards p, and it will become immobile. After it collides with this, it becomes immobile. It doesn't move around. So there's a negative charge formation here at p-type, and from p-type, because from the n-type electrons are leaving, it is leaving behind holes over here. So over here you will get holes, and because the negative charge is leaving, you get a positive charge over here. So what happens at n-type, we have positive, and p-type we have negative. And then in the middle there will be a neutral region that is getting formed, which is called the depletion region. Now depletion region is the part where everything is in equilibrium. There's equilibrium, like everything is at absolute equilibrium. So what happens is, for an electron to move towards p from n, there's a potential over here that it needs to overcome. Sort of like how a photoelectric effect works. There's a frequency after which it will be able to start having a photoelectric current. Before that, if the potential of the electron is lesser than the barrier potential over here, then it will stay here only. It won't be able to move across from the n-type to the p-type. It needs to be more than this. Now the important part is how this works in the... Oh yeah, so we talked about diffusion. So this movement is diffusion, and now because over here minus is formed and plus is formed, there's an electric field that is happening over here. So because of this electric field, what is happening is there's a potential being generated. It's not very high, but due to this electric field, there'll again be movement in the opposite direction, and that is called the drift current. So the depletion region is found where the diffusion and their drift are happening at the exact same rate. So it's right around in the middle. Now we'll talk about how this happens in the forward and reverse bias. So in forward bias is called when you connect a PN junction with the P type towards a positive terminal of a battery and N type towards a negative terminal of a battery. The applied voltage it will drop very negligibly along this PN, but in the middle it is where it will drop significantly, because this is a neutral region. Over here there's charges. This is a neutral region, its resistance will be high, so the potential drop across this depletion region is where everything will happen. So again, over here we have to talk about diffusion and the drift. So what is happening in forward bias? You're opposing the potential of the barrier potential. You're opposing that potential. So because of that, the barrier width, say it was this, it will become this. It will decrease. So if the barrier width is decreasing, basically the barrier, what we can say is that the barrier potential itself is decreasing. An electron needs, like say if an electron needed 5 volts potential, it's way too high. Electron never needs 5 volts potential, but say if it needs 5 volt potential, now when you put it in forward bias of say 3 volts, then what, how about 8 volts, what will happen is it will become 8 minus 5, you need only 3 volts. The new barrier potential will become V minus V0, where V0 is the barrier potential and V is the external voltage. So when this happens, it is easier for an electron from N type to move towards P type once again. At P type, it's for a P type conductor, electron is supposed to be the minority carrier. So when there's an influx of so many more electrons from N type towards P type, we call this movement as the minority carrier injection, because we're giving the minority carrier to the majority carrier of N type towards the minority carrier. So that's what's happening over here. In a reverse bias, the entire thing is actually reversed. I mean, obviously from its name. Let me just rub this. So in this, what is happening? So yeah, over here diffusion thing is followed. When diffusion is followed, you get about like milliamps. You will get your current in forward bias. In reverse bias, we are focusing more on the drift, because what is happening is when the P type is connected to N type and N type is connected to P type, what is happening is the barrier potential and the applied potential is all in the same direction. They are not cancelling each other out. They are actually adding to each other. So what is happening is this barrier potential, this barrier width is actually increasing and becoming bigger. So it's becoming bigger, and an electron needs much higher energy than before to be able to cross this junction. So what is happening is, now the thing is, since our applied voltage is actually increasing, so there's a higher potential difference, so this electric field is actually stronger than before. So you'll have more drift current over here, because if any electron is over here, swept towards its majority carrier. Just give me a second, I need to check something. What is happening in this is that the electric field over here is getting a lot more than it was before. So say if there's a electron at the P type, the electron that is near this junction will be swept by this electric field towards its majority zone. So if the electron which is a minority at P, it will move towards the majority. It will be sent towards the majority. and because of this there is current is happening, and N type the holes will move towards the P type, and this will only happen near the junction. And another thing I need to confirm what happens with this forward. Happens in forward bias. I'll explain it in forward bias once again. So because of that this is happening, and our potential is actually increasing. What it means, barrier width is obviously increasing. Now there comes a point, how much more voltage can you give? If you give too much more voltage, there will come a point where it will reach its maximum, which is called the breakdown voltage. The entire junction will overheat and then it will vanish, like it will disappear. There won't be a PN junction here. The PN junction will break down. And it will be like a normal movement. This happens in forward bias as well. So this, like the voltage you give, even little bit is fine, but if you give way too much, then the PN junction breaks down. Now we need to talk about its graph. Once again, this graph is exactly like how it works in the photoelectric effect, the reverse saturation current, etc., etc. This is a graph, this is the voltage, and this is the I. Okay, so when you're doing it in forward bias, so in forward bias way, I need to be looking at the graph to draw it properly. I want to draw a graph. Yeah. So in a forward bias, what is happening is when you increase the voltage, say over here is 0.2, 0.4. When you're increasing the voltage, the change is very negligible until it reaches one point, say over here, and then it increases sharply. That's called the threshold voltage, and like this is the critical point after which the current increases very sharply. So till this point there's a negligible change. After this it's very big change. After this over here, in the reverse direction, you go like this in the same manner. So the correct graph. It is reverse saturation. Yeah, so in this there is negligible increase. In this the increase is so less that we consider it to be same throughout. It's that less, and this current is called the reverse saturation current. And again after it reaches one point V0, which is called the again it is like very high reverse bias. After this point again it will be sharp increase like this. So this voltage is called breakdown, and over here this voltage will be called the threshold voltage. That's the main difference. Another thing that I forgot to add in forward bias is that when you have the forward bias and when there's a movement of N type towards the P type, it'll be near the junction edge, but because the P type hole is still there even at the junction, like even at the other end of the P type conductor, this will be able to move throughout, like diffuse throughout. So it will move from the junction edge towards this, the other end of the conductor, and that is what is causing the current in this. That's about it. I sincerely hope I don't get confused after explaining it properly, and after that. Thank you so much for tuning in. Where the fuck is the cap? And I will go study Zener diodes and shit now.